Let me thank the organizers for the invitation to this excellent conference. Today we'll tell you about a series of papers based on a collaboration with a great group of people, including two mathematicians. The topic is the Kaluza-Klein spectrum, which is, we all know, is one of the most important pieces of data that associated to a compactification. Let me do that. We need it in holography sometimes, and in certain situations it has actually been computed. And more recently, various bounds have been conjectured, or various behaviors have been conjectured about how these masses behave in certain regimes. So I think it is time to reconsider it from a new light. The focus for a long time was on situations where we could explicitly compute it. This relied usually on the presence of many symmetries in the internal space, or a newer approach relied on, let's say, supersymmetry, extended or maximal even supersymmetry in at least one of the vacua nearby the vacuum that you're considering. But why? So altogether, there are some approaches to compute it explicitly, but there are cases where this can be done explicitly are still few and far between. Why? Well, as a general problem, it is actually quite difficult. If you start doing it, you'll realize that all the different fields that you're reducing start talking to one another, and you have to disentangle the various spin operators. You get usually a problem involving a large number of differential operators. And even just for a simple set of vacua, such as the Freund-Rubin vacua, well, this is a table that I took from a very well-known review on the subject. It takes many, many pages to arrive at this table, where at least you identify the various geometrical operators whose spectrum, whose eigenvalues you have to compute in internal space. And now the real fun actually begins. You have to compute the eigenvalues for these operators. But already the first step of reducing the physical problem to this set of mathematical problems is quite complicated. And here it has been performed, but only for the Freund-Rubin vacua, which maybe in the 80s were exciting, but well, they are also exciting today, but they are really the tip of the iceberg in terms of general vacua, as today we know. So, however, you might despair of being able to make general statements, but in view of what I just said, but you recognize, it has been recognized that there is one case which is sort of universal. Here you recognize, here there was one mass operator relative to the spin 2 tower of fields in lower dimensions that is just an ordinary Laplace-Beltrami, the Laplacian curved space. But for more general, and this was for Rubin vacua, for more general vacua, it is modified, but not too much. It has this expression here. So you need to, the problem for this particular tower fields, for the spin 2 tower, is reduced to computing the eigenvalues of this operator. Again, this is, so this then created another series of led to another series of papers where at least this tower was explicitly computed, not a full Kaluza-Klein list of Kaluza-Klein masses for all fields, but it is for this one, for some set of vacua. But again, it relies on symmetries and some luck. But a different type of spirit is whether we can make general statements about the Kaluza-Klein masses based on the properties of this operator. So, and this is what we're going to do today. If you didn't have that function f, which was just proportional to the warping function, then you will be able to just tap into a long history of mathematical literature, which has indeed put bounds on the eigenvalues of this operator. So, for example, if someone tells you that the internal space has a positive definite Ricci tensor, then well, over the years, stricter and stricter results have been established, and you see that there is only a certain interval which is allowed for the for the lightest mass on any internal space, in terms, in this case, of the diameter. As we will see, there are versions of such bounds also in terms of other properties of the internal space. And this has been known for a long time. However, and I personally knew it, but the presence of this warping function seemingly spoils the fun. You can't just go and use these results. Well, first of all, because here we are talking about Ricci, and Ricci is not the only, well, mainly because because of the presence of the warping and of the other fields, but in particular the warping, you can't reach any definite conclusion about the sign of the Ricci tensor. So what are you going to do? You can't really use these old results. However, more recent ideas, yeah. Good. I was going to define it later, but let me do it now because perhaps it's the best time to do it. So it is the maximum distance among any 2 points in the internal space. So this is what it means. You vary among any 2 points taken at random, and if, the maximum distance you can ever find is called the diameter. Yeah, geodesic, but of course you also need to vary among all the possible. There may be more than one. Yeah, geodesic distance.
Is the warp factor bounded, or can it blow up? Or...
Can what blow up?
The warp factor, is it bounded, or what do you think about?
Excellent. So I will also consider the case where it blows up. So, but this creates a new set of challenges. It typically blows up near physical singularities. Well, unphysical singularities we don't consider in this talk. Typically, for example, for orientifold singularity, it will blow up. So I will tell you what I will do in that situation. So part of the idea is to be able to take care of those situations as well. But you'll see how much I succeed. So very good. So the news, the piece of news that I'm going to tell you about today is that there is a field of geometry that allows you to take into account of that extra bit, the warping function, in a natural way. And this was known as Bakry-Emery geometry, but which was considered already many years ago. But in the last maybe 10 or 15 years, the field has been reinvented and with the confluence of many mathematical ideas in the field of so-called optimal transport. And this is really very active even today. So in fact, this is a limitation in my results today, that the field is not mature enough that everything is known already, but already mature enough to be able, for me to be able to give this talk. And we'll see that the equations of motion involve exactly the combination that mathematicians considered. And perhaps it's not even a coincidence. So first I'm going to tell you how the Einstein equations provide the right mathematical structure the mathematicians need. This might be a longer story, but I'll try to keep it brief in order to then get to the actual results about bounds on the actual concrete results about general bounds on the Kaluza-Klein masses. And then first I'll present an overview, and then I won't give you the full list of results. By now we have quite a few theorems. but I'll give you some applications just so you get the flavor. So the first, I'm going to consider. So let's consider general theory of gravity, which will so with that Einstein-Hilbert term for the graviton and other matter fields, and in general, what you call, or what I call compactification vacuum is space-time of this form, where here you have a maximally symmetric space, maybe ADS in Minkowski of de Sitter, and here you have some internal metric. You consider the equations of motion, they of course look like this, but when you specialize them to this decomposition, they start getting looking a lot more complicated. And already you see part of the problem here, because how are you going to, so even if you know something about the T mu, the sign of T mu, you have here second derivatives of this function here and here. So what are you going to do about those? You can't conclude that Ricci is positive. Of course, for many vacua that we know, for example, for many IDS vacua, our experience tells us that the internal Ricci will be positive definite, but that I can easily give you many counterexamples. So no luck there. However, let's keep going. There is you can use also the part of this equation where you put m and n equals to mu and nu along the space-time, that reduces to a single equation, which is like this. And so in the end, I have achieved at least the feat that I have taken away this particular guy, which created trouble. So then you can start considering at least the sign of this right-hand side here. It turns out that for many theories, this combination is actually non-negative. For example, if you go look at type 2 supergravity, or not just type 2 supergravity, but all the supergravities that we use in string theory, they, for them, for the fields, for the form fields, for example, this is non-negative. We call this the reduced energy condition. It's not really an energy condition in that it relates to, it has to do with both a theory and its compactifications, not the theory per se, but just for sake of speed, we'll call it rec.
How does it depend on what you mean by lambda?
What do you mean? So the lambda, so here was defined by the, this is maximally symmetric, so I say that since it's, no, but this is the lambda of this guy. So this is the lambda of space-time. So since I have used also the internal part of the equation, the external equation of motion, lambda gets back into the internal as well. We check it case by case, not that it follows from any particular principle. You know, it's a finite list of, it's easy to come up with cases that do violate it, and we'll see one at the end. Yes, 2 questions. To the what? I couldn't hear the first part, but like I said, dominant. So it looks similar, of course, but here you see that you, like I said, it has to do, it can only be defined once you know, once you consider compactification, because here, sorry, I should have said it. You see here, this is the dimension of the space-time, and this is the dimension of the full space-time. So it's not a feature of the theory per se, but only of its compactification. Yeah. Sorry, there is a mix here. Here there's the space-time. You see, these are the internal ones, and this is the space-time CD.
When you say D-walk, are you taken out the gauge?
No. I just mean that I, in my life, before this paper, I used to write e to the 2a times the external metric without this parenthesis. I had the same expression. So typically, that's what I call the internal metric. So this one, in my, I call it the word because I have multiplied by e to the minus 2a.
You also consider things where you have gauge fields in this vibration of the internal.
This I wouldn't call a vacuum, because then you need to choose a gauge. This vector will, once you consider its curvature, will single out some directions in space-time. So I personally don't call this a vacuum solution, unless you want to consider two-dimensional solutions. That then we would have to start anew. But okay, so so I got off track. Sorry. Even once you get here, you face two problems. So one is that this second derivative is still here, and the other that in principle you have these brane sources. We have in string theory, for example, brane sources, but even in some other theories you might have defects, and that would create some delta terms. So here I said that this is non-negative for brane sources, but because I consider the delta here, but you might have the feeling that this is not really well defined. So maybe that calls for a better approach. Well, both of these issues I will now consider in the next slide. So you see sources create singularity. This is related to Ibu's question. You see, mathematicians have realized this fact themselves. They would also like to consider spaces, so the Laplacian or similar problems on spaces that have singularities, and they have come up with strategies to deal with that. So the inspiration was to consider functions of well, there are many inspirations, but this is one type of inspiration that they always mention. So let me do that too. So they always say, oh, consider, for example, if you want to generalize to non-smooth functions, this notion of a function that has negative second derivative, what would you do? Well, it's, in this case, it's quite clear. You consider the notion of concavity. This doesn't require, so this makes sense even if the function is not differentiable. And it reduces, it's a generalization, it reduces for a smooth case, for a smooth function to this, but otherwise it's a more general solution that doesn't require you to take any derivatives, so it doesn't care about singularities. There is, so inspired in part by this, let's consider, instead of, let's consider a probability distribution for particles in the internal space. So this would be, or you can also imagine it instead of being not a probability distribution, but just a cloud of particles about which you lack some information. So this quantity here we would naturally call the entropy. This is the von Neumann entropy, and we can consider. Let's consider the because yeah, you see here we were considering second derivative. So let's also consider it here. The second derivative with respect to time would be well, it requires some computation, but after a longish story, you get to this expression, which in particular uses the famous Ricciardo equation. This is how the Ricci appears, and this U is the velocity field of the geodesics. So, well, you stare at this and you conclude that now, so for example, in the Riemannian case, you would conclude that this is positive. And then, if your Ricci is positive definite, then the second derivative would be negative. So you have a concavity now for the entropy function of this cloud of particles as a function of time. We know that entropy is concave in a space of probability distribution, but here we consider it as a function of time. And now, well, perhaps it's clear what I'm going to do. So this would be a possible generalization of what one means by a space of positive non-negative curvature. But okay, still here we have the ordinary Ricci tensor. What if I want to consider more general notions of entropy? So the von Neumann entropy is singled out indeed by a relatively short set of axioms, but considered by Faddeev, for example, in the 50s and 60s. But this has been generalized in various ways. In particular, if you generalize the extensivity to a certain homogeneity, you arrive at something called the Tallis entropy. This is basically related to the Rényi entropy that many of us know and love. It has this expression, and here I have also modified. So first of all, instead of the rho log rho, I have this function of rho, and also instead of considering the usual Riemannian measure, I'm using a weighted Riemannian measure with an extra function. And if I repeat the same steps as above, I am able to prove that instead of having an integral involving the Ricci, I have a different tensor here, which starts looking like the types of tensors that we had in the equations of motion. And this is called the Bakry-Emery curvature. This number n here that I introduced here is called the effective dimension in this business, because it plays a similar role in the computation as the rank of this object here. I can expand if you want, but also in this case then, the natural generalization would be to say that imposing that the sign of this guy now is non-negative, that the sign of this is positive, is equivalent to, or can be generalized by, just looking at the second derivative in time of this Tallis entropy. Now, mathematicians, so this is, I made it simple. So there's a longer story in particular that allows to have something non-zero here, which is what we have after all. We had the term with the cosmological constant. And these mathematicians have formalized this into a condition that they call the Riemannian curvature dimension condition. So this is a class of spaces that is not necessarily smooth. It allows for singularities. It's also interesting to, so you can, along these lines, you can completely reformulate the Einstein equations in this language, but let's go more quickly to the applications. So in particular, the bound that we found earlier from the equations of motion is just telling you now that this Bakry-Emery curvature is larger than a certain value proportional to the cosmological constant. This effective dimension is negative for our application, which looks a little weird, but mathematicians are not unfazed by this. They initially only considered the positive dimension, but lately they have been pushing also this negative dimension case, which is the one we need. So this, like I said, allows us to consider some singularities. And in fact, the ones that, so brane singularities are exactly in this class. So this is can be proven as a theorem. And the crucial element in this is that the behavior of particles around the brane singularity is as in, so they get attracted by the singularity. Whereas if you consider something like a singularity of an O-plane, this doesn't happen, they get repelled, and as a consequence, this is outside, the O-planes are outside this class. Fortunately, there are some bounds that don't even require a notion of curvature. There are not so many, but some do exist, and for those we, asking around, so we ended up with this even larger class of spaces that mathematicians can consider. Okay, so this was some very quick introduction to the math. This optimal transport is broad, very large topic, but sorry for my oversimplification. Let's get to the actual results. So there are several. We'll see several types of results. Bounds from above, bounds from below, and more often on the lightest mass, but sometimes also on the larger ones. As I already implied, there are different degrees of generality. Sometimes we can only work on smooth spaces, but we have seen that often we can involve brane singularities as well. And we have seen already some bounds in terms, so in the introduction, a couple of bounds for the unwarped case in terms of the diameter, but you can also consider bounds in terms of the internal volume, which is fun because it is related weighted volume, so the integral of this particular power, the warping function, which is fun because it's related to the directed to the Planck mass. And then my favorite is the class of bounds that involves the so-called Cheeger constant. This Cheeger constant has something to do with the shape of the internal space, not just with the size. And it detects whether, so this is small when your space is almost separated into two pieces. So you consider all the possible objects of the same dimension as your space, and then you look at the weighted volume for the boundary and for the thing itself. And for example, in this picture, I have chosen one that for which this ratio looks quite small, and you can achieve this precisely because the space has a small neck. So this is what this Cheeger constant is telling you. So for example, in this Pant's decomposition that appeared even in some talks that is famous for Riemann surfaces, that has to do with the length of those necks, one of which is one of the Frenkel-Nielsen coordinates. So here's an overview. The one for the Planck mass is fun, but it only works for the smooth case, and moreover involves an upper bound on the warping, which is bad in view of what Ibu was asking. So, for example, wouldn't apply to O-plane singularities. But there are others, in particular in the Cheeger case, you achieve a lot more success. And there are also several bounds involving the diameter. So this is an overview. Let's, since I have very few minutes, let's look at some concrete results and some applications already. So one is to so-called gravity localization, which has nothing to do with the gravity localization in the previous talk. This is an older story, an older notion, which comes from, for example, the Randall-Sundrum model, or its analog with the cosmological constant, which is called the Kark-Randall model. Let me explain what this is in the next slide. So if you have a model where the weighted volume of your space is infinity, there is no massless graviton. So, for example, if your internal space is non-compact and this is non-normalizable, this is what you will find. But famously in the Randall-Sundrum model, this is finite even if your space is non-compact, but sometimes this doesn't work either. Then there is no massless graviton, but you can ask, okay, let me see whether at least the next one is going to be very light, in which case we might not see the difference in the universe. And well, we give, so here we have a general result about what the smallest mass can be. So if you see from here that if your space has a small neck, like I said earlier, then the smallest mass is indeed very small. and you can have a very light graviton. There is an analog also for the compact case, which might be relevant for so-called bigravity models, where you want to have two massless and a light massive graviton. So in fact, for these models, if you really want to claim that you don't see the internal dimensions, not only you would like to have a light graviton, but also the higher modes are much heavier, so that you really don't detect them. And this also you can achieve with this other type of bound. So this involves a higher analog of the Cheeger constant that detects whether you have also more than one neck, let's say. So in a simple space like this, you don't. You only have one, so you can immediately conclude almost without any computations that there is a hierarchy, that you can see the smallest, the lightest graviton, but not all the others.
In this case, the light graviton lives in the bubble region, right?
Yeah, very good. So yeah, so that's the intuition. So in fact, maybe it's even clearer what happens in the compact case, where in the limit where you split off the two halves, you have two massless gravitons, so to speak, but then you reconnect them, and one of them remains, and the other is massive, but with a small mass. And with the non-compact case, only the light one remains. Thank you. So there is a, before you think that this is all a fantasy, there is a class of vacua that has been considered by, in particular, it wasn't worked out by him, but he pointed out that these vacua do provide buffers and lambdas. They pointed out that this may indeed give rise to localization, and we conclude that indeed it does. And moreover, we give a reason. We don't just compute the gravitons, but we have a general reason. There's also a fun fact that the Cheeger constant has a, you then discover that it has a holographic interpretation in terms of the free energies of the CFTs involved. Okay, so there was also a general notion of something called the spin 2 conjecture, which implied that that this could not happen, that if you make the smallest graviton light, then all the others have to be light as well. And we showed that this does hold, but in a certain regime, when the first is above a certain threshold. And below that threshold, that fails, as we saw for the model before. Okay, let me conclude in the very little time I have left with another application to scale separation. So this is this will surprise no one, but it's a rigorous confirmation of something we expect. What is this issue? So for many antidisruptor vacua, it is known that for many of the most better known vacua, the size of the internal space is actually comparable. The typical the diameter, let's say, of the internal space is actually comparable to the curvature radius of ADS, which does not sound very realistic. One would like to have the scale of the cosmological constant to be much smaller than the scale of the Kaluza-Klein modes. Of course, also ADS is not realistic, but well, this has given rise to a lot of speculation on how, in what generality, one can actually achieve a hierarchy between the cosmological constant scale and the Kaluza-Klein scale. And our methods seem to be well suited to this problem. So, for example, we can find, so this now generalizes those bounds that we saw from the 80s on the original Laplacian to, first of all, warping, but also singularities. And you can find both a bound involving the Cheeger constant and one involving the diameter. There's a certain function here, but you see that in a certain regime it goes like one over the diameter as the previous bound in the introduction, which I guess is confirms the intuition that we all had. So as an application, so one famous solution that exhibits scale separation is the so-called DGKT solution, the Wolf et al. This basically works because it violates that energy condition that I had long ago. And given that, problem, that feature allows it to use an internal Ricci flat space. So there are various complaints about this solution, but let's say there is at least an approximate uplift. And if you estimate the Chi constant in that approximate uplift, you see that it confirms the fact that the solution achieves indeed scale separation. There is another example, maybe, this is due to Thomas van Riet and collaborators, maybe he'll talk about it, and here you can even apply the other bound, the diameter. And lastly, actually, if you are violating the REC, there is an even simpler way. You don't need much to achieve this, but I thought I would point this out. So if you use the Casimir energy, that also violates the REC, and it allows you to have a flat internal space. And then you have a very simple solution, which achieves scale separation very easily. And the arguments I gave also allow you to conclude that that indeed it achieves scale separation. So in conclusion, we saw that the Einstein equations imply bound on the not on the Ricci tensor, but on this combination of the Ricci tensor with the warping. And moreover, the same computations that reveal the importance of this tensor also give you a way to include singularities, and in particular brane singularities. Using this, we are able to show some upper and lower bounds on the spin 2 KK masses, and we saw a couple of applications. Thank you for your time.
Thanks for a nice talk. Questions?
Maybe I misunderstood, but did you say that there was an example of a compactification with a finite number of massive spin 2 guys separated arbitrarily from the tower?
Yes.
I see. Could you say a little bit? I'm shocked, yes.
There is more than one, in fact. So, you know, instead, okay. So this is one example. No. Right. These Bacchus-Lavdas solutions are, well, so if you remember the old Kirk-Randall model, where, of course, there was only one extra dimension, not 6, but the idea is very similar. There was a brane there, and then, so gravity, they found a way so that, so the reason, sorry for everyone else, the reason this is called gravity localization is that typically if you consider a brane inside the higher dimensions, gravity will sort of leak out. I mean, it will see that there are extra dimensions. It will not, the graviton will not just remain near the brane. It will want to go outside. But in certain models, it does remain, the graviton does remain close to the brane. So here this is achieved because of the shape of this space. So here this is an example where only one is light and one massive, and the others are above. There are also cases where, so this you see, the gravity dual is of a CFT3, which communicates with the CFT4 on one side, but you can also have a CFT sandwich. Forget maybe Van Ransom.
Is the theory effectively classical? Is the S-matrix, for instance, of these massive gravitons classical, or does it involve?
No, this is a supergravity solution, so you don't need to involve gravity. Like
the S-matrix will scale faster than S squared at fixed t, which I thought was somehow problematic in the regular.
Do you? Only in a certain regime, I think.
There are these longitudinal gravitons. You know, there's the transverse and the longitudinal. And the longitudinal guys, they grow very fast, right?
So this is an analysis for the TT gravitons.
Okay, thanks a lot.
Wait, I'm looking forward to.
Thanks. Is there a role for supersymmetry in what you explained? And I would have said that the spectrum of the masses depends both on the action that you're studying and the vacuum you're expanding about. How is this result universal?
This is a result for the spin 2 tower. So the other towers, a priori, I know nothing about. But in case vacuum has the supersymmetry, they will be related to it. So to this tower. So this is what I can answer. So this is the main role for supersymmetry that I can see. So I mentioned some cases where the spin 2 tower has been computed as physicity, and there part of the reason for it was that the vacua were supersymmetric. They had a lot of supersymmetry, and they gave you then some information about the rest of the towers as well. Almost all of it, in fact, and you could read off from that quite a bit. So this is the main role for supersymmetry. So you might also imagine that there is something that you can say about the top, the spin 3 halves. But okay, we can talk about that later.
Going back to this case for a moment where you have one light massive spin 2 and the rest are kind of gapped. There are these older conjectures that you can't have a consistent truncation in a classical supergravity where you just have a finite number of massive spin 2s. Am I supposed to think of this as a counterexample to that, or are the other spin 2s not parametrically heavy?
Where you can't have a consistent truncation?
Right, I mean consistent truncations with finite numbers of massive spin 2s were believed not to exist, attempted to be constructed, those failed. So this is a counterexample or not?
But again, so above, so when you go up, eventually we'll see them.
Right. But it sounds like, how heavy are the other? Are they parametrically heavy or they're just?
You can make them as, so it's more that this one is parametrically small. The other ones will remain order 1, let's say.
Okay.
In the
parametrically small, meaning almost massless?
1 over L. Yeah, one is almost massless.
Okay, I see.
So in that sense, I don't think they will fail. And this might be related to.
Is the homogeneous space flat space or ABS?
Is there a homogeneous space?
I thought your setup was homogeneous plus internal.
You mean the external space?
Yeah.
This is ABS.
Maybe flat space.
These are dual to. Wait, I thought this was part of. Okay, maybe I misunderstood your question. So indeed, this is dual to a CFT setup. These are the duals to the Hanani-Witten or Gayotto-Witten, whatever.
Yeah, would there be a way of getting flat space plus something with just finite number of massive spin 2 particles?
Okay. So one thing is to find the result. So the results apply, the general results apply, but that's only half the problem, right? Then you have to look for a solution that where the internal space has this shape, which is a whole different kettle of fish, and I have no idea. Probably I would doubt it, but we can talk about. By the way, so there is even. You can also consider the Maldacena-Nunez type of solutions where they have, of course, a Riemann surface inside the solution. And once you have a Riemann surface, part of the, not all, but part of the spin 2 spectrum will be dictated by what happens on the Riemann surface. And for that, you don't even need me. There are several studies on the spectrum of Riemann surfaces, and they have found previously that if you make the next of the Pan's decomposition small, indeed you'll find as many light masses as you wish. Not as many, sorry. 2G minus 1 masses, where G is the genus. So I can provide for generalizations, and that would be then for ABS5, for example, if you want to talk about Maldacena-Nunez. Or BBBW also. Same story applies.
Maybe one more question if there is. If not, let's thank Alessandro again.